lesson today is about maxima minima problems. And at the end of this lesson, you must be able to analyze and solve maxima minima problems with ease and accuracy. Okay, here are some steps suggested to help us analyze correctly maxima minima problems. Now, I will just be illustrating how it is done working with some examples. Okay, let us consider this problem. A box is to be made from a piece of cardboard 16 inches by 10 inches by cutting equal squares out of the corners and turning up the sides. Now find the volume of the largest box that can be made this way. So the first step to do is to work out some illustration, and what we have here is the rectangular piece of cardboard 16 by 10. The next step is to cut equal squares out of the corners, and the dimension of the square is set at x by x, so that when these squares are cut from the corners, then the remaining section of the cardboard will have this dimension here given by 16 minus 2x. Over here is 10 minus 2x, and when we flip these extra edges up, then we get this box. So the resultant figure will just be this box with base dimension of 16 minus 2x, 10 minus 2x, and height of x. And if we represent this as L, this dimension W, and this one as H, then the volume of the box will just be given by product of LWH. And if we will be substituting these expressions accordingly, then volume function would be defined as such and would simplify to V equal to 160x minus 52x squared plus 4x cubed. Now, of course, the necessary condition for the maximum or the minimum value of the function to occur would be at points where the derivative is equal to 0. So we work on the derivative dv dx, giving us 160 minus 104x plus 12x squared. So the next step would be to set the derivative dv dx equal to 0. Hence we have 160 minus 104x plus 12x squared is equal to 0. Next is to determine values of x that will satisfy this equation. We just have here a quadratic equation, so you can make use of any of the techniques or the methods that we can use to solve quadratic equations. Now what is illustrated here is the use of the factoring technique. So on that basis, you are able to determine x values that would render this particular expression 0, and that will be at x equal to 2 and at x equal to 20 over 3. Now, at which value of x do we satisfy or do we realize maximum volume? Then we can verify that using either the first derivative or the second derivative test. So here we're illustrating the use of the second derivative test to verify whether we obtain maximum or minimum value of the volume at x equal to 2. So the second derivative of the function v with respect to x will just be given by negative 104 plus 24x, and if we substitute 2 in place of x in this expression, that will give a second derivative value of negative 56. Okay, now if you will do the same with x equal to 20 over 3, then you can easily verify that the second derivative value at 20 over 3 would be positive. Okay, so which of this value will maximize v? It is that value that would render second derivative negative. Hence, we claim now that volume is maximum at x equal to 2, and that maximum volume is determined by simply substituting 2 in place of x in this particular expression here, to give us v equal to 144 cubic inches. So this value of v is the maximum volume realized at x equal to 2. Okay, let us consider this second example. It says, find the altitude of the largest circular cylinder that can be inscribed in a circular cone of radius r equal to 5 inches and height h equal to 10 inches. Again, an illustration would be very helpful in visualizing the problem as well as set up our working equations. So here is this illustration to the problem. We have the right circular cone over here with height of 10 inches and base radius of 5 inches. And inscribed in here is a circular cylinder, okay, where the height of the cylinder is represented by y and its base radius by x. Now it would be better if we can view we can have a view of this illustration as a plane curve, and we can do that by considering the cross section of this figure. So we cut this figure through the center line to come up with an illustration like this. So the triangle is just the cross section of the cone and the rectangle for the cylinder, and then you can easily verify that the dimensions that we have reflected here are the same as those that are given in the earlier figure. Okay, and it is easier to work on the relationship of x and y using this figure here, considering that in this figure we take note of triangles that are similar. Okay, this big right triangle here of dimension 5, okay, base radius of 5 and height of 10 is similar to this small one here. And for this small one, or for this small right triangle over here, this dimension is x. It is as long as this one. So this is x, and this one is 10 minus y. So that using the principle of corresponding ratio of corresponding sides of similar triangles are equal, then the ratio of these horizontal sides would be equal to the ratio of the altitude. So we will have here x is to 5 as is 10 minus y is to 10. Now, since this problem is involved in determining the largest circular cylinder that can be inscribed in a right circular cone, then the objective function will be on maximizing the volume of the circular cylinder with the volume of the circular cylinder given by product of base area times its altitude, or we have that equal to pi r squared h, or equal to pi x squared y, where x is the radius, the base radius of the cylinder, and y is the altitude. Okay, now this volume function is dependent on two variables x and y. So there you have an option of expressing the volume to be function of x only or of y only by making use of this relationship that we have set up earlier. And in this solution, we opted to express the volume function of y only. So we substitute out x using in place of this the expression 10 minus y over 2. And thus the volume function will just be defined as such, or you can multiply the factors together to come up with this as your volume function of y. Okay, now again, satisfying the condition of maximum volume occurring at a point where the first derivative is equal to 0, then your next step would be to differentiate v with respect to y and come up with this expression of pi over 4 times the quantity 100 minus 40y plus 3y squared. Okay, your next step would be to equate the first derivative of v with respect to y to 0. So this expression is equated to 0, and solving now for the values of y that will satisfy this equation, we come up with y equal to 10 over 3 and y equal to 10 inches. Okay, which of these values would maximize the volume of the cylinder can be determined and can be verified either using the first derivative or the second derivative test. So here we are using again the second derivative test to determine optimality of the solution at y equal to 10 over 3. So this is the second derivative of v with respect to y, and substituting 10 over 3 in y will give us the second derivative value equal to negative pi. This value being negative will tell you that volume is maximum at 10 divided by 3. Of course, you can verify optimality of the solution at y equal to 10. And at y equal to 10, the second derivative value will be positive. So that would mean that volume would be minimum at y equal to 10. So this particular problem is addressed with y equal to 10 over 3 or approximately 3.33, maximizing the volume of the right circular cylinder. Okay, to recap what we have discussed, it is the concept of the derivative as a slope of the tangent line to a point on the curve that is used in solving application problems involving maxima and minima. Okay, and that the critical values, the first derivative value will be equal to 0. Now, for whatever values of the variables that you have solved, you always have to test for optimality of your solution. So I'll see you in our next lesson.